This is a video from section 12.5, and we're going to find the equation of a line in 3 space, and we'll call the line L. Okay, so what we're going to do is we're going to let P naught, which is equal to X naught, Y naught, Z naught, be a specific point on the line. And so for sake of argument, and I'm going to be referring back to this drawing quite a bit, I'm going to put P naught right here. Okay? Then I'm going to let P, which is XYZ, be any other point on the line. So P naught is specific, P is general. And so what I'm going to do is I'm going to put P right here. Okay, so we're going to go back again. Let R naught and R, so these are vectors, and let these guys be the position vectors of P naught and P respectively. And what I mean by position vectors is that the initial point is at the origin. And so when I go back, I'll use blue. So I'm going to start at the origin, and I'm going to draw a vector out to P naught, and we're going to call that vector, I'll just draw an arrow here, R naught. And I'm going to draw a vector out to P, and I'm going to call that vector R. So we have R naught and we have R. And then what I'm going to do is I'm going to let A represent the vector P naught P. And if we go back, that's right on the line. Okay? So that vector is located on the line. And so we'll call that A. So let me do that. And let me come over here. By vector addition, we can say R naught plus A is equal to R. So you could either use the triangle law for vector addition, or you can use the parallelogram, and either which way you're going to see that R naught plus A is equal to R. Now, what we're going to do is we're going to let V be a vector that is parallel to A. And to be parallel, what that means is this. There exists a scalar T such that A is equal to TV. And so if I go back to the picture, now V is drawn so that it's parallel to A. So we'll put V right there. And one thing to keep in mind is if V is parallel to A, and A is located on the line by design, right? It's the vector that connects up P naught to P. If the vector V is parallel to A, it must be parallel to the line. Okay? And so, therefore, if I replace A with TV, I get R equals R naught plus TV. Like so. Now, R equals R naught plus TV represents the vector equation of the line. Now, do you guys remember in two-space, you need a slope and a point to get the equation of a line? Well, in three-space, the difference is you need to have a specific point on the line and a vector that's parallel to the line. So I always remember this as point plus scalar multiple of vector. And so you need a vector parallel to the line, and you need a specific point on the line, and if you have both, you can get the equation of a line. And now, let's check this out. Suppose I had the following. And I'll make a comment about the line in a minute. Suppose V is ABC. And so that implies if I take TV, I get TA, TB, TC. So therefore, and before we get even to that, also R is the position vector XYZ. R naught is X naught, Y naught, Z naught. Okay? Now, remember that R, the vector form of a line, is equal to R naught plus TV. And so what I'm going to do is I'm going to make some substitutions. And so R is XYZ, and R naught is X naught, Y naught, Z naught, plus TV, which is TA, TB, TC. Now, let's go to the next page. And so we have XYZ is equal to X naught plus TA, Y naught plus TB, and Z naught plus TC. And so remember, I just combined the vectors on the right-hand side of the equation. And you combine vectors by adding their respective components. Okay? And now, two vectors are the same if their corresponding components are equal. Now, what does that mean? Well, it turns out that says X equals X naught plus TA, Y equals Y naught plus TB, and Z equals Z naught plus TC, where T is a real number. Now, these equations are called the parametric equations of the line. Okay? They're called parametric equations. So when they're written as a vector, this is a vector equation right here. Or actually, well, I'll actually use this. That's the vector form of a line when you have r equals r naught plus tv. If we go back, these are called parametric equations. There's 3 equations. Now, in those parametric equations, suppose I solve for t. And now we have to assume t is not 0. Or, excuse me, we have to assume that a is not 0 for this to make sense. And so if I solve for t, can we agree that t is x minus x naught divided by a? And if I have y equals y naught plus bt, that implies t is y minus y naught divided by b. And if I have z equals z naught plus ct, that implies t is z minus z naught over c. And here's the thing. If t equals x minus x naught over a, and t equals y minus y naught over b, and t equals z minus z naught over c, what that tells me is the following. That says that x minus x naught divided by a is equal to y minus y naught over b, which is z minus z naught divided by c. And what these are called, these equations are called the symmetric equations. Of the line. And A, B, and C are the direction numbers. And maybe I should add, they're the direction numbers of the line. Okay, I think this is a good stopping point. And then in another video, I'll make examples where we find equations of lines using the vector form, parametric equations, and the symmetric form. All right, thank you.